Hi, and thank you for joining us today for the latest Technology Network's mass spectrometry webinar. This technical webinar will explore the latest advances in mass spectrometry research through a program of presentations from leading scientists and experts. My name is George Hammond, conference producer for Technology Networks, and I'm thrilled to be here to moderate the event today. I'm also incredibly pleased to introduce Dr. Diane Turner as your first speaker, who will be discussing her talk, Hydrogen as a Carrier Gas for GCMS. Dr. Turner is a director and senior consultant at Anthias Consulting Limited, providing training and consultancy in analytical techniques. She started her career as an analytical chemist, later gaining significant experience as an application chemist, and has over 25 years of experience in chromatography and mass spectrometry-related techniques. She is also the president of the Royal Society of Chemistry Analytical Sciences Community Council and chair of the Analytical Chemistry Trust Fund. A warm welcome to you, Diane. Following the presentation, we will have a Q&A session, and we welcome any questions you may have. Please ask questions using the Q&A system to the right-hand side of the video player. Please also feel free to navigate over to our literature section, where you can download the latest resources from the sponsors of today's webinar. If you experience any technical issues during the webinar, please click the chat icon in the bottom right corner to request support. Now, without further ado, I will hand over to Dr. Turner to begin her presentation.
Wonderful. Many thanks, George. So as John mentioned, my presentation today is on the use of hydrogen as a carrier gas for GCMS. This kind of area has gained significant attention over the last couple of years, mostly because of increases and also in price for helium. And also because of the shortage of helium as well, with labs not being able to get cylinders of helium for, well, I hear some of them, it might be months at a time. And of course, that's very, very worrying. So there is kind of quite a drive towards hydrogen as a carrier gas. So in this presentation, I just want to look at some of the benefits of using hydrogen as a carrier gas, and of course, some of the negative type things, and also have a look at some of the improvements in analytical instrumentation, and especially in gas chromatography and mass spectrometry, that the manufacturers have been doing in order to reduce the negative effects of using hydrogen as a carrier gas. So let's first of all just think about types of carrier gases used in gas chromatography, not necessarily in GCMS, but just in GC in general. So the reason why we use a carrier gas to start with is to transport the vaporized sample onto the GC column, through the analytical column and into the detector. And one of the key purposes of that is to be very good at doing that, not to discriminate and leave some compounds behind, but also not to react with the analytes. So whenever you perform an analysis, the key thing is we really want to see what was originally in our sample. We don't want any changes to occur, especially if we're trying to identify those compounds. And of course, that's one of the key things of using GCMS, to actually do identification of unknown compounds. So types of gases which are commonly used in gas chromatography are nitrogen, helium, hydrogen, argon, and argon methane mixtures. So let's have a look at each of those in a bit more detail, and then think about which ones we could be using in GCMS and which ones we definitely wouldn't be. So to think about that, we need to think about the two main properties of our carrier gases. So first of all, we have our diffusivity. So this is the diffusion speed of an analyte between the carrier gas and the stationary phase, and determines our optimal flow rate. So if we think about then our molecules in our GC column, what are we trying to get them to do? So we want them to go into the mobile phase, because that now allows them to move through our GC column, but we also need them to go back into that stationary phase as well. Otherwise, they'll just fly through the column and we'll get no separation. And of course, when you go into that stationary phase, we'll be getting some interactions occurring. So therefore, if we have a carrier gas which has got good diffusivity, that means that it can very easily move those molecules into the stationary phase, out of the stationary phase, into the stationary phase, out of the stationary phase, to then get them progressing through the column, but also as well to get that good separation actually occurring as well. Now, if we go and run our column flow too quickly, what's going to happen is that the molecules, when they go into the mobile phase, they're going to be basically flushed down through the column, and they can't make that next interaction site in the column. And that means that we're going to reduce that resolution. I always think of it as kind of like people, a group of sprinters. who are running in the Olympics, and they all end up at the finish line at a very, very similar time. But if you now start to put hurdles in the way, then that's going to get that separation. And the more hurdles we've got in the way, the better the separation is going to be. So if then they are taking bigger jumps and then missing, jumping over 2 hurdles at once rather than 1, of course, we're not going to get such good separation in there. So we need to make sure that we're not flowing our carrier gas too fast, so that we can make sure that all of our molecules get into in all of those individual interaction sites in our stationary phase. We also think about our viscosity. So our viscosity, then when we have more viscous carrier gases, then we're going to require more higher pressures actually in our system. So, because of course we need to get that flow rate through the column. Now, viscosity is proportional to the temperature of the oven. Now, in most of the GC analysis, what we're going to do is we're going to be separating a wide range of volatilities of different compounds in there. So we're going to start with the oven cool, and then we're going to heat the oven up to higher temperatures. And as we increase that temperature, the viscosity of that carrier gas will increase. So that means that we're generally, to maintain the flow rate going through the column, we're going to need to increase our pressures. So, you've already got quite high pressures because we've got quite a viscous carrier gas, we're going to have to use even higher pressures. And the problem, of course, one of the main problems with gas chromatography is leaks. And leaks are going to be more likely to occur the higher the pressures that we're actually using. And that can affect our introduction into the GC inlet. So when we inject our sample, we don't want that sample escaping and squirting back out with our carrier gas if it's not sealed properly. So again, that is more likely to happen if we've got very high pressures in there as well. Also as well, of course, then viscosity that compresses the gas at the head of the column, slowing our linear velocities. So if we think about our diffusivity and our viscosity in terms of the common carrier gases used that we've just mentioned, in terms of diffusivity, nitrogen has a much lower diffusivity than helium, which is approximately the same as hydrogen. That means that we can't use very high flow rates with nitrogen, because otherwise it's going to miss those interaction sites. So it's not going to be very good at moving those molecules backwards and forwards between the mobiles and stationary phases unless we're using quite slow flow rates. In terms of our viscosity, then, hydrogen is much less viscous carrier gas than helium, which is approximately equal to our nitrogen. So that means that when we're using hydrogen as a carrier gas, we use much lower pressures than we do with helium and nitrogen. So that, of course, is then going to affect our analysis and our flow rates and our separation. So the Van Diemen's curve, I'm sure you've all thought about and all heard about, and this is an equation which relates the column resolving power to the flow and the kinetic parameters that cause our band broadening. So if we go and look at our different gases, then they have a different profile in there. So we have on our x-axis the average linear velocity, and that is us in centimeters per second, and on the y-axis, we have the height equivalent of a theoretical plate. So that then is going to affect our column efficiency. So when we go and look at nitrogen as a carrier gas then, so we can see that so first of all, our optimal column efficiency is at the lowest point on our y-axis. So for nitrogen, it's at this point here. For helium, it's this point here. And for our hydrogen, this is this point here. So when we look at all these types of gases, first of all, what do we notice in terms of where that bottom point actually is? And we can see then that our most our carrier gas, which is going to cause improve and cause the best column efficiency, is going to be nitrogen. So that's got the lowest point just there. And then we've got our hydrogen over here, and then we've got our helium. Now, there's not a huge amount of difference. We still can get very good separations with helium as a carrier gas, and indeed we do. However, it's not quite as efficient as with our nitrogen and hydrogen. However, as we can see with our nitrogen then, we can only get that optimal efficiency when we are using low flow rates. So for nitrogen, the average linear velocity is about 12 centimeters per second for a standard column, which is about 30 meters long with a 0.25 millimeter internal diameter. So that's quite a slow flow rate. Now also notice that if we go slightly too fast, or slightly too slow, we get a very significant drop in that column efficiency. So not only then do we have to use slow flow rates with our nitrogen, but also we need to be really, if we want the best column efficiency, we need to be really quite accurate in terms of our flow rate in there as well. Now, in terms of the left-hand side, so we've talked about the problems on the right-hand side. If we go a bit too fast, we don't get such good separations, etc. But on the left-hand side, what happens is that if the flow rate is not fast enough, what we are getting is band broadening. So in particular, we get a lot of longitudinal diffusion. So if we have all of our molecules nice and close together to get our lovely sharp peaks, which is what we want to be doing, then actually they're not all staying together and they don't really like each other. And what they're going to be doing is diffusing in both directions. And that will then cause our broad peaks. So we'll get our band broadening in there. Now, of course, then, as we get our band broadening, we're going to get less separation and we're going to get lower sensitivity of our analysis as well, because we have a nice tall sharp peak, which is then going low and broad, which is then going to be difficult to then see at low concentrations above the baseline. So we don't want to go too slowly either, because that really increases our longitudinal diffusion. So if we then move to helium, okay, the bottom point is not quite so low as nitrogen, but what we can see is, number one, is that we can run and have a higher average linear velocity. So the optimal in our standard column is about 35 centimeters per second. But also we can see it's much, much broader. So if we go slightly too slow, or if we go even slightly faster, then we're not going to get a big drop off in our column efficiency. Now, when we move to hydrogen, then we are going to be using an even higher average linear velocity to get our optimal flow rate, our average linear velocity for the best separation and best column efficiency. So that is about 60 centimeters per second as for a standard GC column. So, and also when we look at this, it's even broader still. So we can go really, really, really fast in terms of our column efficiency. So in terms of then developing our methods when we're trying to get our optimal average linear velocity through our analytical column, then of course, again, then when we go away from nitrogen to helium and hydrogen, and especially when we go to hydrogen, we can use quite a wide range of different average linear velocities and get good, really good column efficiency out there. So in terms of conclusion for speed of analysis then, so hydrogen will allow us to use higher flow rates than helium, which is higher than nitrogen. But if we wanted to get the best resolution, nitrogen will give us the best resolution over hydrogen, which is going to give us better resolution than our helium in there. So again, it's about what we're trying to do in terms of our analysis. So let's then think about our different types of carrier gases. So we also mentioned argon, which gives us a very similar funding to plot to our nitrogen. And argon and nitrogen are generally used with both packed and plot columns. So that's our capillary columns with a porous layer, open tubular columns. That's a solid stationary phase. And they're especially useful in gas and volatile analysis. Argon and methane mixtures are very much used in isothermal electron capture detectors because they give us better sensitivity. Both of these gases are inert, so they are useful for thermally for labile compounds which are easily hydrogenated. However, they do have higher molecular weight, and we do have to have higher GC head pressures for these, and they have higher viscosity at higher temperatures. So quite often then, these types of carrier gases are using either low temperature programming, so not to go very high because of the increase in pressure, but also as well for isothermal analyses as well, so particularly useful in gas analysis. One of the problems when we try to use these gases with in a mass spectrometer is that they can saturate the detector because they've got quite a low mass. So argon has got a low mass of 40 and nitrogen is 28. And if you're doing quite volatiles analysis with GCMS, then of course they're going to give you a very, very high background and going to saturate that detector. In fact, you wouldn't be able to acquire at those lower masses if you're using those as a carrier gas. Also, the other problem is they have a higher proton affinity and lower ionization energy. So we can get adverse detector interactions through the ARH plus ion in our mass spectrometers as well. So that does mean that generally we don't use these types of carrier gases with mass spectrometers. They have a low optimal flow rate and steep deep to plot. So therefore, as we mentioned just now, our flow is critical. So the optimal linear velocity is about 8 to 16 centimeters a second with standard columns. So as I mentioned earlier, the most common type of carrier gas is using helium because it can be used with all different types of columns. And it's also very, very common with GCMS. It enables us to have high resolution temperature program GC. It doesn't give us quite as good a column efficiency as the other types of carrier gas, but it still gives us very good separations. It is slightly less efficient. And also we can run it with faster flows than nitrogen, but then slower than with hydrogen. The viscosity is approximately 2 times higher than hydrogen, and the diffusivity is similar to hydrogen. And as we mentioned just now, the optimal linear velocity is around about 20 to 40 centimeters per second with our standard column sets. It's got a very low molecular weight, so that means it's very good when we're using it with mass spectrometers, and we can go down to quite a very low mass range when we're scanning to then identify for more volatile compounds. It's inert, that means it's not going to react with our compounds of interest, and it's also non-flammable, so that's relatively safe. The biggest drawback, of course, with helium is, especially over the last couple of years, is the cost. So it's very, very expensive, and of course the supply is not quite so good and reliable as it used to be. So a lot of methods, a lot of laboratories are now moving across to hydrogen as a carrier gas. It's a reactive gas, so generally it's not used with compact columns, but with capillary columns it is becoming more common. Partly because of the cost, but also partly as well because it is more efficient than helium at high velocities. So we can get shorter run times and also better separations as well, as we'll see in a minute. The optimal linear velocity is over a wider range than with our nitrogen, so we can go a little bit faster and faster than nitrogen and faster than helium as well, with a typical optimal linear velocity between 40 and 60 centimeters per second with our standard column set. It is the least viscous carrier gas. That means that when to get those flow rates, to get that good average linear velocity, which is quite fast, we actually are using quite very low pressures. And it's got a very high diffusivity, so it's very good at moving those molecules backwards and forwards. And of course, that enables us then to have those higher flow rates. It's much cheaper than helium. And even cheaper still is actually buying a hydrogen generator. These can then sit underneath the bench. They are much better in terms of health and safety because hydrogen is a flammable gas, which is a bit of a problem. So therefore, having a hydrogen generator underneath the bench is going to be better from the health and safety aspect, but also as well, the generators can produce very high purity gas. In fact, quite often when using hydrogen from a generator with things like flame ionization detectors, the lit offset, which is basically the level of when, of the signal from the FID, when the GC thinks it is going to shut down, actually has to be reduced when using hydrogen from a generator, because it's much purer and it's got lower noise levels as well. Biggest problem there, of course, is that it's flammable, and even bigger still from a chemistry point of view is it is reactive. So generally we always used to think of carrier gases in GC have to be inert, but of course hydrogen is not an inert type of carrier gas. So therefore we can get reactions occurring, and reactions can then reduce the sensitivity of our methods, because some of those molecules are going to be changing and are going to get lost. So that means that our signal will not be as big, as good, and our sensitivity is then reduced with our system. So we can get catalytic hydrogenation occurring, and also things like dechlorination. So we're going to have a look at those later on in this presentation. So that's our key types of carrier gases. So one of the things that we've kind of identified is that we can get faster separation, and of course we can get better resolution with certain types of carrier gas. So if we look just here at a particular chromatogram and separation, this is actually more on the GC side than GCMS, then what we can see then in our first chromatogram is a very standard method using nitrogen as a carrier gas. So here of the flow rate, the average linear velocity is 11.7 centimeters per second. So it's within that optimal range for nitrogen as a carrier gas. And of course, nitrogen is very efficient, so we get very good separation. And we can see that our resolution between our two peaks just here is 1.76. So remember, with resolution calculations, 1.5 or greater means that it is baseline resolved, meaning that we can then integrate those peaks from baseline to baseline, and that means that we get better accuracy in terms of our integration of our area to then provide quantitation results. However, the problem with this one is that we have a runtime of 24.5 minutes, which is quite a long runtime. And if you wanted to improve that, what could you do? So first of all, rather than change anything, we could just go, well, let's go and run our nitrogen at a higher average linear velocity. So now we increase that to 20 centimeters per second, which is not quite double. And of course, we get our faster runtime. So we get an earlier retention time now, going from 24.5 minutes to 17.4 minutes. However, though, the problem is now it's not at the optimal flow rate, so we're too fast up the side of that Van Dieter curve. So we now have got a resolution and it's not baseline resolved. So our resolution is 1.33. So we go, okay, we've got a much faster runtime, but now what else can we do? So of course, then the nitrogen is not providing us the speed that we want through our analytical column to then get that faster analysis. So we could go and switch to helium as a carrier gas. So we can go to our optimal flow rate for helium, remember, which is between 20 and 40 centimeters per second. So here is showing it with 23.2 centimeters per second. And again, that's faster still. So we're getting a shorter runtime of 13 minutes. And because now we've got that optimal average linear velocity for helium, our resolution has improved again. So now we have a resolution back to 1.67, not quite so good as nitrogen, because remember, it hasn't got such a lower curve in the Van Dieter curve, but it's still baseline resolved, which is what we want. But we could go still 13 minutes with not more than 10 minutes off, which is absolutely great. But can we speed it up still? And then we can go and try it with our hydrogen. So this is running again at our optimal linear velocity, which remember is between 40 and 60 centimeters per second. And this one is running with 48 centimeters per second. Now we can speed it up even more, and we have a much shorter runtime of 6.2 minutes. So that is a quarter of what it was in the original method. But you think, right, okay, going really that fast, can we really get the resolution that we want? And yes, we can. So this has got a baseline resolution of 1.65. Now, one of the key things, of course, is that when you go to higher flow rates and faster analysis times, then of course we're going to get less band broadening. And that means we're going to get sharper peaks as well. And so one of the things going to hydrogen as a carrier gas and much shorter run times is you really have to look at peaks in a slightly different way. So first of all, when you look at this, your peaks are very narrow. So the peaks are very narrow. That means that they are taller because, of course, we've got the same area in there. So, of course, they're much sharper. They're going to give us much better signal to noise as well, as long, of course, as hydrogen is not reacting with those compounds. But also as well, when you quickly look at it, you're going, is it really separated? So when you go to these narrow peaks, you really have to zoom in on the chromatogram to go, yes, these peaks are still baseline resolved. When you're still looking at it from that full view, it might not look like it actually is. The other key thing as well is look at the retention times of your peaks. So again, then you're looking at, usually with normal chromatography, you're going and looking at the retention times of your peaks that you're separating, and there could be a half a minute between them or even maybe more. When we're getting to much faster analyses and much sharper peaks, the differences in those retention times are going to be much smaller. So that means that again, then you go, are they really separated? But yes, they are chromatographically, but you kind of have to change your way of thinking. Now, this really also influences, of course, things like your acquisition rates, especially on your GCMS instrument. So if you're doing selected ion monitoring and you've got your groups for those different compounds, then of course the widths of those different groups, so from the start time of when it's acquiring the data and just for the ions for those peaks within that group to the stop time, those are going to be much shorter. Also, of course, you're going to have that actually you need to be even more accurate in of the timings of those, especially if you go and trim your column and your peaks come out earlier, that you are going to have to go and update those times. So those SIM groups, the selected alarm monitoring group, actual windows as well. So that's another thing kind of again going with our GCMS of actually how it's affecting our method, is that we have to be much more precise in terms of our timings of things like SIM groups with our GCMS, and also of course maintaining and updating those SIM groups as well. And of course, if you have timed events for your integration, that's also going to be affected as well, and you have to be very accurate. So we have to kind of, again, when we go to those fast chromatography, kind of change our way of thinking and change our way of looking at our chromatograms. But we can see our advantages there of moving to helium, moving to hydrogen in terms of our run times. And of course, if you're analysing hundreds of compounds, so saving of this run time, this time actually means you can get much higher throughput, especially in your contract laboratory where you need high throughput and lots of samples being analysed. So that's one of the pros of going to our hydrogen as a carrier gas. One of the negative things is, of course, flammable. And over the years, I've spoken to a lot of people going, we're just not allowed to go to hydrogen as a carrier gas because it is dangerous and it is flammable. So one of the first things you need to do before switching to hydrogen as a carrier gas is first of all check that your GCMS is actually suitable for use with hydrogen as a carrier gas. Older instruments might not be. So therefore then if something does happen, there are some really good videos actually on YouTube when GCs or GCMSs are actually filled with hydrogen and ignited, and you can just see like a little bit of a dent in the door for newer instruments. Of course, though, if we're using older instruments, they might not have that same health and safety kind of built into using hydrogen as a carrier gas within those. So do check with the supplier, the manufacturer of your instrumentation, before you just go, right, let's go and switch over to hydrogen as a carrier gas. If you're using flame ionization detectors already in your laboratory, then you're going to be running hydrogen through your GC and into your FID at about 30+ mils per minute. So, of course, that goes in through the bottom of your FID. So just only actually flows around where the ferrule is, which is sealing the column actually into the bottom of your FID. So of course you've already got hydrogen going in there, and of course if there is a leak at that particular point on that knot of ferrule on the base of your FID, that is going to be getting hydrogen already into your oven, and we're going to be using much higher flow rates of 30 mils plus, mils per minute plus. Whereas of course carrier gases, we are using lower flow rates in there, so maybe a few mils per minute. So that's kind of, again, one thing. Okay, so it's going through the whole of our column, and of course we've got multiple potential leak points because we've got the nut and the ferrule installing our column into the inlet as well as into our mass spec transfer line as well. However, of course, you're less likely to get a leak out of hydrogen in your mass spec transfer line because you have got a vacuum in your mass spectrometer. So actually it's then sucking that hydrogen through. So in some ways, actually, it's less likely you're going to get a leak into your GC oven. Other things that you can think about is attaching any split vents to a ventilation system. So again, then if, for example, on your inlet, if you've got a high split ratio, you'll be putting a reasonable amount of hydrogen into the laboratory air. So if you could attach that to your ventilation system, that's going to take that away. As I mentioned already, hydrogen generators are generally safer than cylinders in the laboratory, and you can also get hydrogen sensors, ones for both to go inside the GC oven if you're worried about it there, but also in the laboratory as well, especially if you're using your instrument is based in quite a small room as well, then that is advisable to go and get that. So in terms of our safety then, we can minimise any problems in terms of the fact that we're using hydrogen, which is a flammable gas. Now, one of the other things, of course, is our negatives is, first of all, our reactivity. So it is not an inert gas, hydrogen, and also in terms of our flow rates as well when we now come to a GCMS. So we've already discussed then that hydrogen we can run at higher average linear velocities, and it's much broader. However, though, if we do run it too slowly, of course, we are going to compromise our column efficiency and our separation. So when we go to GCMS, of course, one of the limiting factors in our GCMS in terms of the flow rate is our pumping system within the mass spectrometer. So therefore, depending on what you have, a diffusion pump might be kind of up to about maximum 1.5 mils per minute. But if you go over 1 mil per minute, you are going to reduce your sensitivity. In terms of turbo pumps, if you have quite a small one, that might be quite similar in terms of maximum flow rate for your column flow. However, though, going to a bigger turbo, that can affect, go up to much higher flow rates. And so if you have more turbos, maybe you have 2 turbos on your mass spectrometer, or maybe you have just the one, but you need to know what the optimal flow rate is, because of course the turbo needs to be able to, so whatever you're pumping into your mass spectrometers to get a good vacuum, then you need to be able to pump it away very effectively. And of course, if we don't have such a good vacuum, it is going to massively affect our sensitivity of our mass spectrometer. So as well as making sure that your GCMS is suitable for using hydrogen as a carrier gas, then also check your vacuum system as well. And if you're buying a new one, I do recommend using high performance turbo pumps, which then gives you a more, and you can go to higher flow rates in your mass spectrometer, which you're probably going to want to do to really take the full advantage of using hydrogen as a carrier gas. So again, then back to the health and safety part of it. So again, understanding your system is really, really important. So knowing where your gas is coming from, where your gas is going to within your GCMS system. So this is a typical schematic of just a basic GCMS instrument. So what we have is our gas source. So that could be a cylinder of your hydrogen, or even better still, is using a gas generator underneath the bench under the instrument, or near the instrument. And of course, then the gas has to get then through a series of a series of tubing and piping to actually get to your instrument in the first place. So again, then thinking about the health and safety aspect is every fitting is a potential leak point. So again, from the health and safety aspect, you need to make sure that you are regularly checking all of those fittings as you go through there to make sure that you don't have any leaks. And that it's more likely to have leaks coming out with a GCMS between the gas source and the back of the instrument, or going from the back of the instrument into the inlet, then because of course the closer we get to the mass spectrometer, the closer we're getting to the vacuum, so we're more likely to have a leak going into our systems at those points. So again, then making sure that it's leak tight all the way through to the instrument is really important. And traps and filters are really important as well to making sure it's clean. So again, if you're using a hydrogen generator, then of course usually you'll be producing hydrogen from water. So it's a must then to have additional traps and filters on the back of your GC. So there will be traps and filters in your generator, but I find that they can become saturated quite easily, and it's much better to then go and have an indicating moisture trap on the back of your GCMS, on the back of your GC, and also an indicating oxygen trap as well, because of course if you take water and you're producing hydrogen from it, what is left is oxygen. So again, then oxygen, of course, can damage your stationary phase, and water can damage certain types of stationary phases as well. And both of them would reduce the sensitivity of your mass spectrometer. So that's another thing that I would always put into place, is at a minimum a moisture and oxygen filters or indicating traps at the back of your instrument. And again, weekly go and check them to make sure they're not being saturated. Same though if it's from the cylinder as well. Put a hydrocarbon trap in there as well, just to make sure your background is low as well. So then thinking about our gas flow going through the system. So of course, when we then we take our source, our cylinder or a generator, it goes through plumbing, goes through the traps and filters, and then goes through our electronic pressure control modules in the back of the GC. We then have a 16th inch tubing usually that goes to our GC inlet, and then of course in the inlet is where we connect our column. So then we have then our main analytical column within our GC oven, and of course then it goes through our heated transfer line into our mass spectrometer. So again then tracing them within the instrument as well. So remember, the further away from the mass spectrometer is, the more likely you are to then have a leak coming out of the system. So make sure that you've got a good leak detector and regularly go and check fittings. Even if you haven't disconnected them or anything like that, or changed your column, you should be still checking them on a regular basis, especially inside of the GC oven, because heating, cooling is going to then loosen those nuts and ferrules. So understand where your gas is coming from and going to as well. Now, if you are having an older system, and you are now converting from helium to hydrogen as a carrier gas, one of the first things you'll probably find is that you have a lot of background and high baselines. So hydrogen is very, very good at cleaning out the system. So, you know, with cars, you could go and every now and again, you can pick basically cleaning fuel inside your car, and that basically gets rid of all the dirt and stuff that's been left and contaminating within your system to get your engine performing much better. Again, then it's almost like that when you're putting hydrogen in through your system. So it could take, and I have had instruments to do this, it could take up to 2 weeks for the hydrogen to clean and purge the whole system out. And of course, the further that your gas flow path is, then the more cleaning it's actually going to go and take. So do be aware of that as well. And a lot of people are really shocked when they first start using hydrogen as a carrier gas. It's like we suddenly got all this crud which is kind of coming out of their system, and it can take a while to settle down and purge all of that out. So do be prepared for that as well, and don't be surprised if you see a lot of really high baselines and a lot of background contamination coming actually through. So again, then thinking about that carrier gas flow path is also important on there. Now, in terms of our reactivity then, so of course I've mentioned that you can get reactions occurring between the hydrogen carrier gas and your analytes. Now think about, for a reaction to occur, what is our conditions that is going to be more likely to? Number one is heat. So if anything in any areas which are heated, and the higher the temperature, the more likely reactions are going to occur. And the second thing is having a catalytic site for that reaction to occur as well. So that could be, again, in your sample flow path, any sites which are going to be active. So therefore, they're not deactivated. Deactivation, of course, then will really help to reduce then your compound from getting stuck at that active site, especially if that's in a hot area, and of course then it's being swept through by the hydrogen, and of course then it's more likely for reactions to occur. So again, then we need to think then about our sample flow path and where these are going to happen. So if we got a standard liquid autosampler, we're going to inject our sample into the inlet. It vaporizes our sample, transfers those analytes onto the head of the column. We're separating those analytes on our column, and of course those separated analytes elute into our mass spectrometer, where they're first ionized. We get our fragment for ions forming. We then separating those fragments and molecular ions based on a mass to charge ratio through our mass analyzer, like a quadrupole, and then we go into our ion detector, where then our results are produce a signal, and that is then recorded by a chromatogram, by a computer, to produce our chromatogram, and then of course each of those peaks will give us a mass spectrum. So if we think about the inlet, the sample flow path part of this, so what we have on this particular one is we have our inlet. So of course, then having a deactivated inlet liners is really important. Then of course we have our column. So we need to have a column which is going to be very robust. It's going to be deactivated. So any areas of the inside of the column where we don't have any stationary phase need to be very deactivated as well. So we can get a range of columns which are very inert. So we want to have the deactivation through there, and of course then into our ion source as well. Our analytes are actually going to go through. So again, then we can think about deactivating or having an ion source which is going to be very deactivated to again reduce the likelihood of those reactions occurring. So we can look at our sample flow path from a deactivation point of view, and now we can think about our sample flow path from the temperature point of view. So again, then on our temperatures, we're going to have a hot inlet. So therefore, again, then, is that going to be too hot? We should always optimize our inlet temperature so that it's hot enough to vaporize the highest molecular weight compound, but not too high that we're going to then transfer our dirt onto the column as well from that sample. And of course, it's even more important to get the right temperature with when you're using hydrogen as a carrier gas. Again, with our column then as well, we don't need to be going to really, really high temperatures. And generally, actually, with hydrogen as a carrier gas, because it's more diffusive, actually we can, and it can get those molecules into the mobile phase at actually lower temperatures. So actually, we don't need to use such higher temperatures when we're using hydrogen as a carrier gas. So we've got the oven temperature program and final temperatures, and then we've got a heated transfer line going into the mass spectrometer. Generally, the heated transfer line does not need to be as high as the final oven temperature, and that is because, of course, at the end you've got your vacuum sucking your molecules through that transfer line. So my rule of thumb is about 40 degrees below your final oven temperature. So if your compound's coming out at the oven at 300 degrees C, then you probably only need your transfer line to be in 260. But if they are coming out at 350 degrees C, the transfer line needs to be about 310 degrees C. So again, then think about your molecules are moving through there. That's a heated zone. So again, if it's too high, you're going to get more likely having reactions occurring. And then, of course, we move into our ion source. So again, then our ion source is heated. It's not as hot as a column, but this is where, again, we're going to be then ionizing, usually using electron ionization. But again, we don't want reactions actually occurring within the ion source. All we want to do is knock out that electron. So again, temperature is also something that needs to be optimized in that point. But of course, once those ions are formed, now also as it moves into our mass analyzer, then the hydrogen carrier gas should have been sucked away at that point. So in the ion source, you have your hydrogen carrier gas, of course, that is coming out of the end of the column with your analyte molecules. So the ion source, again, is a very likely place for reactions to occur. So once we kind of think about the setup, we can look at it from a deactivation point of view, and we can think of it as from a temperature point of view to then reduce that likelihood of reactions. And that then gives us some really good indications of where we need to go and optimize our method for using hydrogen as a carrier gas. Also, of course, then we have our autosampler. So this is just showing a standard liquid autosampler. However, though, you might be using something like a headspace instrument or a thermal desorption instrument, pyrolysis, etc. So, of course, you then need to think about deactivation through those, and also, of course, any temperatures through those as well. So, for example, if you had a thermal desorption instrument, you then be thinking about this, okay, your tubes are fine in your tube autosampler. However, they will have our focusing trap, and then, of course, all of the tubing as well in between there. When we put our introduce our sample from our TD tube all the way through to our GC. So of course that all also needs to be highly deactivated, and we also need to think about as well, are we going to get reactions occurring with the sorbents that we're using in our TD tubes or in our focusing traps as well? So that's also another important area to think about. So if you are using a particular type of autosampler, then you should be thinking about that as well. So when we think about gas chromatography, there are certain compounds which are problem ones. So thermally labile compounds decompose in a hot system. High molecular weight compounds are subject to discrimination due to their lower volatility. Trace analytes are more difficult to detect, particularly in dirty samples. And active compounds, we get increased interaction, irreversible absorption, or we get catalytic degradation, basically getting them to break down through our system. So then when we think about our hydrogen as a carrier gas, of course, then what areas we're going to be thinking about? So if we're using lower temperatures with our hydrogen as a carrier gas, then it might be a little bit better for thermally labile compounds. However, some thermally labile compounds, again, are more likely to react with hydrogen as a carrier gas. High molecular weight compounds shouldn't be so much of a problem. Again, trace analyze, if they are thermally labile or active compounds, again, they could be more of a problem. Especially if we are getting some reaction, of course, it's going to be even harder to set those particular compounds. And of course, again, those active compounds also are more likely then to go and react. So of course, problem compounds, they can still be analysed using gas chromatography. We do need just more care when we're choosing, optimizing and maintaining the analytical system. So for example, thermally labile compounds, we can get around that by using a cold injection technique, where you basically inject it into an inlet that's at a cool temperature below the boiling point of the solvent, and then ramp that up to transfer the analytes onto the column. So again, by going to hydrogen as a carrier gas, we still need to be thinking about these problem type of compounds. And again, our active compounds, again, we're going to be using deactivation, which we've already identified we need to be using with hydrogen as a carrier gas. So what are the manufacturers doing about it? So we've talked about then kind of the type of inlet, we've talked about columns, and we've talked about temperatures. So one of the things which, then you can get consumables, you can get different inlet liners which are deactivated, you can get columns which are very inert and very deactivated, and of course we can optimize our methods in terms of all our temperatures. But one area that we can't really do a lot about is our ion source. So some of the manufacturers then are going across to making sure that their ion sources are as inert as possible. So I'm going to show you some data, some information from which is courtesy of Agilent Technologies, which is then focusing on their hydro-inert ion source, which I've been working on quite a lot this year, developing some applications using hydrogen as a carrier gas, and I'll tell you a little bit more about that towards the end of the presentation. So we have got our compounds in here. So we've got hydrogen as a carrier gas, and this is looking at nitrobenzene as conversion. So one of our problem compounds in using hydrogen as a carrier gas is this nitrobenzene. So what we've got then is on our left-hand side, this is our mass spectrum for nitrobenzene. And we can see that some of the key ions, we've got our 77 in there, but other key ions is our 93 and our 123 just in here. However, though, in the ion source, again, which is heated, and we've got our hydrogen going a carrier gas, then we can get that nitrobenzene converting to aniline. So we can see that basically with our little formula, which is just over here. So we have our nitrobenzene just here, and we have our hydrogen, the carrier gas, we have heat, and we have a catalyst. So that's basically, catalyst is usually an active site within our system, and that will then go and convert over to aniline just over here. And what we can see just here then is that we then are getting our 93 has got a lot bigger, so it should be a small ion in the mass spectrum on the left, but it's actually quite a large ion then on the right. And our 123 has got much smaller, and our 77 has also got much smaller, which is showing that basically this is a mass spectrum of our aniline, so that's being converted across. So what about other compounds? Is it just fixed and a problem with nitrobenzene or nitrogen compounds? Absolutely not. So there are certain compound classes which are very difficult to do using hydrogen as a carrier gas. So we've got our nitro compounds like our nitrobenzene, our phennitrothione, our ethylfluorine just in there, and this means that then with hydrogen carrier gas as a conventional GCMS source, then what's happening is that then it's basically converting it and it's giving us unacceptable results. So I'd like to just have a look at some applications, which comes from actually courtesy of Agilent Technologies, of looking at some of these problem compounds which can react in the ion source of the mass spectrometer. So the first one I want to have a look at is our nitrobenzene conversion. So if we look on the left-hand side, just over here for our NIST. So I want to have a look at some problem compounds which can go and react with hydrogen as a carrier gas within the ion source. So the data I'm going to show you is from Agilent Technologies, and the first one we want to have a look at is nitrobenzene conversion. So when we look at the mass spectrum for nitrobenzene over here on the left-hand side, we can see that, and this is of course produced, we're using helium as a carrier gas, we can see that we've got a very strong molecular ion, 123, and we've got quite a small 93 ion and a large 77 ion, and that's what we're going to be seeing basically with our nitrobenzene. However, when we look and think about the reactions which are occurring for nitrobenzene, then this is with hydrogen as a carrier gas. And of course, in the ion source, we are applying heat and we might not have inert surfaces. So therefore, our active surfaces are basically providing a catalyst for this reaction to occur. So what we'll get then is that conversion from our nitrobenzene to our aniline with hydrogen as a carrier gas. And if we go and look at the mass spectrum for that particular compound then of the aniline and what it's converted to, we can see that then our 123 ion here has greatly reduced in size. And our 93 ion has greatly increased in size due to that conversion. And again, our 77 ion has greatly reduced in size. So that we know if we're analysing and injecting and separating our nitrobenzene in there, the left-hand side is what we should see and what we do see using helium as a carrier gas, but a lot of it is being converted to this aniline on the right-hand side, which again is showing us a mass spectrum of aniline just in there. And this is kind of a problem. Is it just the nitrobenzene? No, there's several different classes of compounds which are problems in our ion source when using hydrogen as a carrier gas. So we've got our nitro compounds I just mentioned, so nitrobenzene, but also things like phennitrothione and ethylfluorine, and that will get that reaction if we're using hydrogen as a carrier gas with a conventional GCMS ion source. Other heavily chlorinated compounds like DDT, endrin, heptachlor, BHC compounds and things like pentachlorophenol, so a lot of things like pesticides, etc., also will be going and dechlorinating. We'll have a look at that in a bit more detail in a minute. Polycyclic aromatic hydrocarbons, that can cause some problems in those, but it's a bit of a neutral one, so it doesn't really have too much of a change or a problem. Alkanes greater than C24, like tetratricontin, etc. So these are those high molecular weight compounds, again, is neutral. So we're not getting any difference in changes. So other pesticides like deltamethrin, fipronil, permethrin, captan, again, we're getting reactions occurring, so giving us unacceptable results. Flavour and fragrance compounds like musk ketone, musk ambrette, linalool, again, are getting reactions occurring. But volatile organic compounds like dioxanes, trichloromethane, bromodichloromethane, they're much, much smaller molecules. So we're getting actually less reactions with those. We're getting some, still some good results with those. But it's these problem ones which are, kind of these higher molecular weight, larger compounds, which are then going and reacting with hydrogen as a carrier gas. So I said earlier about some of the manufacturers are actually improving their instrumentation to then not only work with hydrogen from a health and safety point of view, but also now from the chemistry point of view as well. So this is the adjuvant hydroinert source for hydrogen carrier gas on GCMS, which I've been working with quite a lot actually this year and been getting some really good results. So I'll talk more about that a little bit later. But it's been especially developed to reduce the loss of sensitivity and spectral anomalies that we see in the MS ion source due to that reaction with hydrogen. So it's more inert, so that reduces catalytic sites for reactions to occur with hydrogen in the ion source. Compounds are also less likely to stick. So therefore then, again, if they're less likely to stick, then ion source temperatures also can be lower than you can conventionally using those conventional temperatures in the ion source. And also as well, being highly deactivated also means that it can also reduce the source cleaning and maintenance, but of course along hand in hand with our hydrogen as a carrier gas, as we mentioned earlier as well. So let's go and have a look now at results with the nitrobenzene with this inert hydroinert source. So the existing extraction source, remember, gave us a large 93 and a small 123, which is showing nitroaniline, not a nitrobenzene. But then when we go and use this as the source, the hydroinert source, then what we're going to see then is we get a much increased 123, which is where it should be, which is our molecular ion, a reduced 93. So remember, we do see 93 anyway, but it's much smaller. And of course, we got our larger 77 ion in there. So therefore, the hydroinert source for this particular application is preventing hydrogenation. But for other compounds as well, it can really help to reduce it as well. What about other reactions that can occur in the ion source with using hydrogen as a carrier gas? So we've got our hydrogen cleavage reactions. I'm going to use captan as our example just in here. So we can see our captan's got a mass to charge ratio of 299, and with our conventional with our conventional source with hydrogen, then we can basically see that we are not seeing some of the compound, while we're seeing some additional ions in there that really shouldn't be present. So for example, our extracted mass spectrum is 150.9 just in here, and not our 149, and NIST, it's showing a 149 ion just in there. So we're kind of like then we can see that, yeah, so on the left, we can see a greater abundance of 151 iron in there, which is created without our hydro-inert iron source. Whereas, of course, over here on the and we can see very little of our 149 just there next to that 151. But if we go and use our hydro-inert iron source, which is over here, we can see now that we haven't got, or we got very little of that 151, and we can see a larger amount of our 194 iron just over here. So what's happening on the left-hand side is we're getting that 151, which is the cleavage of the nitrogen sulfur bond and the addition of 2 hydrogens on there. And we basically see then that's after the cleavage, and we get our dechlorination product on the right-hand side just over there as well. So that's giving us our 195, which is at the top over here as well. So we're getting from our captan, which is the molecule in the middle, we're getting our dechlorination, which produces the 195 on the right-hand side, and our cleavage of the nitrogen sulfur bond, an addition of 2 hydrogens, which is giving us our 151 on the left-hand side, just on there. So again, then with the hydrogen-inert source, it may be not quite so good as the nitrobenzene, but we are getting less hydrogenation occurring, and therefore much better NIST match scores with that. What about with calibrations then? So, you know, what is occurring with this? So when we can see at the top, we can first of all is, does the hydro-inert enable us still to have very good calibration curves across the range of 0.1 to 100 micrograms per mil? And we can see that here we've got examples of using helium with a traditional iron source, which is at the top, and of course then at the bottom is using hydrogens at carrier gas with our hydro-inert iron source just down there. When we go and examine our average RF percentage RSDs, we can see with our helium, it's got a 6.33, and for our nitrobenzene with the hydrogen and hydro-inert source and the 9mm lens, then that's giving us a RSD of 6.59. So yeah, very, very similar. So slightly worse, but it's exactly in the same ballpark just on there. What about the sensitivity then, the comparison, the iron source with the hydrogen as a carrier gas just in here? So we can see in here then, be looking at our mass spectra, looking at our particular ions just on here, and we can see that we've got carbon tetrachloride on the left-hand side. So this is using a conventional ion source with hydrogen, whereas we go and use our hydro-inert on the right-hand side, of course, with hydrogen, we're getting a much larger ion for the particular, the key ion, just for the key peak, just in there for carbon tetrachloride. So we're getting much less reactions occurring, less of that dechlorination that we can see in there, and that is giving us a much bigger peak. And also as well, we go and look at something like bromoform as well. Again, we can see on the left-hand side a conventional source with hydrogen. It's quite a small peak, whereas when we look at our hydro-inert source on the right-hand side, it's a much better signal to noise. So more than double is the signal to noise actually for both of those compounds. So again, then you can see that looking at the different compounds we've looked at here, that some of them we then has a massive effect on those compounds, and some of them it does have some effect, but it is a smaller effect on those. So it is very, very compound specific. So now if we go and just look back at that table that we looked at before, when now thinking and pulling in the information about using that hydro-inert ion source from Agilent with our hydrogen carrier gas. Again, then, so what we've got now is our nitrogen compounds was unacceptable before, but now it's differentiating. So it's very much, some of them are, you've got now back to where it is with helium. Others, we might still have a little bit of drop in sensitivity from our reactions, but it's much improved. Heavily chlorinated compounds is exactly the same. Again, the same as with the nitro compounds, we've got a massive improvement. Our PAHs and our alkanes, that we've got the same, of course, which they weren't affected. And again, we've got our pesticides, fragrance and flavour compounds, and also our VOCs as well are improving in there as well. So more thinking then about our thermal desorption. So again, this is an example from Marks International. So of switching to hydrogen as a carrier gas. So again, with a newer instrumentation, the thermal desorption instruments, again, they've made improvements so that we're not getting those reactions occurring with hydrogen as a carrier gas as you would be if you were using older types of instrumentation. So it's an example of looking at PAHs with thermal desorption, and our sample size here is 480 litres, which was drawn through the thermal desorption tube. So what we can see then is we've got then our information. So we've got our limits of quantitation is 0.077 nanograms per meter for all compounds, and limits of detection is 0.023 nanograms per meter cubed for all compounds, or less for each of those. So again, then we've really got a kind of we're not losing anything by going to our hydrogen as a carrier gas with thermal desorption as well. But again, if you have an older instrument, you need to check with the manufacturers whether or not it is suitable or not. So finally, I just want to summarize some of the pros of using hydrogen as a carrier gas, but also as well some of the recommendations. So with some of the pros, of course, are things like it cleans the ion source during use for GCMS. We can also use lower temperatures. So again, looking at each stage from inlets, columns, transfer lines, and of course our ion source as well. They all need optimizing in terms of our temperatures. So of course, if we're using lower temperatures, then of course we're going to get less likelihood to have reactions. But hydrogen, because it's high diffusivity, it means that we can use those lower temperatures to start with. Think about moving to more efficient columns. So a standard GCMS column is 30 meter 0.25.25. So think about going to a 20 meter 0.18.18, and that's going to give you actually even better separations as well. Use gas filters, especially with hydrogen generators, so that moisture and oxygen is really important. Also use hydrocarbons as well. You remember you might need to allow the system to bake out for longer to get rid of all of that dirt, because of course hydrogen will be kind of reacting and burning things off through the system. So of course, if you just switched across to hydrogen, it might take a while for your baseline to come down. Beware of your maximum flow rates with your MS vacuum system, so know what your optimal flow rates are. Otherwise, okay, you're getting sharper peaks, faster analysis, etc., better signal to noise, but if the vacuum's not so good, you might actually result in having a lower signal to noise. Avoid chlorinated solvents and hot inlets. So for example, dichloromethane plus hot inlet plus hydrogen, plus especially if you've got any tiny amounts of water in there. So trace water in your dichloromethane, you're going to get HCl being produced, which is not good for GC columns. Avoid heavily chlorinated compounds because of that dechlorination potential. And again, think about inertness everywhere through your whole system. And again, the same thing with our nitro compounds. So again, if you are going to switch to hydrogen, if you do have nitro compounds or chlorinated compounds, then you are probably going to get some problems with those, and you might get a bit of a drop in sensitivity. So really optimizing it. And even with optimization, you might not get back to your full sensitivity that you do have with helium. But the key thing is it good enough for your application? And that's what you really need to go and ask. So as I mentioned earlier, so I've been working quite a lot with the hydroinert ion source this year, and we basically, with narrowing smaller columns, etc., as well, using the Intuvo system, we've managed to get down to our PCBs and PAHs in one run down to less than 6 minutes. And the PCBs, the polychlorinated biphenyls, yeah, okay, we do have a bit of reactivity, and they're still tiny a little bit, but we still get this sensitivity which is required for the analysis. So I'd just like to thank you very much for listening today, and I'd like to thank Technology Networks for inviting me to give this presentation. I'd like to thank Vanessa Abercrombie from Agilent Technologies for providing the information from Agilent, and Marks International, Aaron Davies and Helen Martin for providing the information from Marks International. My colleagues at Anthias Consulting, and also at the Open University in the School of Physical Sciences, the Oral Society of Chemistry, Analytical Science Community, PACN and Books, and also the Community for Analytical Measurement Science. So thank you very much for listening, and do you have any questions?
Thank you so much, Dr. Turner, for that incredibly insightful presentation. You are truly an expert in this field. We're likely to receive a lot of questions, so I'm now going to move on to the Q&A session. If you'd like to submit a question to our speaker, you should enter your question into the box on the right-hand side of your screen and click send. We will, of course, answer as many questions as possible during the time available. And I can see that we've already received some questions. So your first question, Dr. Turner, is which applications would you say definitely aren't suitable for analysis by GCMS with hydrogen as the carrier gas?
So I think, some of the applications we have mentioned are things like pesticides analysis or anything that's got chlorinated or nitro groups in there. I mean, it doesn't mean that you can't do them, but you are going to have to do a lot more of optimization. If you're analyzing something like just hydrocarbons, you're going to likely see a very little difference, especially with saturated hydrocarbons. Of course, you still need to optimize in terms of flow rates, temperatures, etc. as well, but there's going to be less problems in changing across. But certainly if you are doing things like any pesticides, any poly species, etc., that you need to really then think about, okay, do I have a suitable instrument? Is it does everything as deactivated as possible, and before you then start on that journey? So actually at the Open University we actually have a GCMS which has got both helium and hydrogen connected to it, so we can develop a method in helium as a carrier gas, and then we can go and switch over to hydrogen as a carrier gas, and we can then improve and tweak the method, and we can directly compare our helium method with our hydrogen method, and that is really, really useful. So if you are switching to hydrogen as a carrier gas, then think about actually, can you have both connected so you can actually really do those direct comparisons, because of course it's exactly the same instrument. So definitely recommend that if possible as well. Thank you.
That's perfect. Thank you so much. And sticking on that subject, do you have any tips on approaching my instrument supplier about switching to hydrogen?
So it's just switching to hydrogen. Yes, absolutely. I mean, again, there are a lot of the manufacturers have a lot of application notes now for when using their instruments for hydrogen as a carrier gas. But again, some manufacturers haven't quite got there as yet. So again, consider what instrumentation you have. If it's quite a simple liquid chromatography system and it's relatively new, it's very likely that you'll be able to upgrade it. And again, like for example, I think on some kind of my slightly old or mid-age Agilent GCMSs, it actually has on the little cover, actually, if you're using hydrogen as a carrier gas over the ion source, take off this cover, etc. So you know that it is suitable for using hydrogen as a carrier gas. But again, making sure you know what your ion source actually is at the moment, and can you upgrade it to like a hydroinert ion source, I think is key. And also as well, thinking about your turbo as well. So again, then if you've got like a diffusion pump, you probably will not be able to get the full benefit as using hydrogen as a carrier gas and using those higher flow rates with just a diffusion pump. So go and consider that, but gather all the information first, have a look on their website, look for application notes, and then go and approach them when you have got all of that information and you just want some extra reassurance, etc. Like, for example, is my GCMS suitable? Do you have a document which will then help me to then convert my instrument from helium to hydrogen as a carrier gas? But always double check and never go and do it unless you're 100% certain that it is suitable.
That's amazing. Thank you so much, Diane. And we've got time for, I believe, one final question today, which is, my boss says that hydrogen is too dangerous as a carrier gas. How can I persuade him otherwise?
Well, no, first of all, I think I mentioned in my presentation is, first of all, do you have hydrogen in your lab already? If you do have hydrogen in the laboratory, then thinking again about, okay, how often are the fittings, etc., all leak checked to make sure that there's no hydrogen leaking out of it? And again, especially if it goes outside, is in the summer, your tubing will go and expand on your fittings, and in the autumn, they go and contract. So that's the most likely time to go and it leaks. And if it's a real concern, then they should be checking those on a very regular basis. If you have things like a flame ionization detector in your lab, then you're always already going to have hydrogen in there. You're already going to be using it, and you're actually going to be using it at much higher flow rates than you've already got. So again, then think about your ventilation, think about kind of, again, do you have things like a leak checker? so which then can detect small amounts of like things like hydrogen or any type of gas which is coming out of your fittings, and do you regularly check those? So again, if you are thinking of converting across it, you've got to think about it from the health and safety point of view, but you've also got to think about it from the chemistry point of view. So again, then gathering information, there's lots of different sources as I've just already mentioned, and putting together kind of like document or email, etc. to them, thinking about all the pros, thinking about all the cons, and then go and discuss it with them is the key thing. But again, if you are in an environment where, you know, for example, in a production facility, then hydrogen is probably not going to be used anyway. So it's very unlikely that you'll be able to use hydrogen as a carrier gas. But also think about it from the purse string side of point of view of how much money is it going to save the lab by going to it. And quite often people will upgrade to a hydrogen generator for two reasons. Number one is that it produces more higher purity of hydrogen gas, but also as well from the health and safety aspect, and also of course the cost as well. So the cost of actually having cylinders, I know labs that have basically saved them or made the money back by having a hydrogen generator for 3 months in terms of how much they're actually paying for cylinder rental, etc. as well. So again, it depends on what type of boss you have. Do they want to hear it from the chemistry point of view? Do they want to hear it from the health and safety point of view? Or do they want to hear it from the money side of it? So you've got to then think about your argument from either of those ways.
That is fantastic. Thank you so much. And thank you for joining us today. But unfortunately, that is all that we have time for. But it's been an absolute pleasure to have you present with us. And we really appreciate your time today.
Brilliant. Thank you very much.
A certificate of attendance is available to download from the handouts tab on the right-hand side of the webinar platform. And please feel free to navigate over to our literature section, where you can download the latest resources from the sponsors of today's webinar. This webinar will now be made available on demand, so if you have any friends, family, or colleagues that you think may be interested in this webinar, please feel free to share the link with them. And that just leaves me to say thank you once again, Dr. Turner, and we will be back soon with the next talk.
Thank you.